Hello, this is Schweitzer, and this is a level 2 vectors and projectile motion chapter. We're looking at the standard I can break two or more vectors into components and add them to form a new resultant. Alright, so here's a little tutorial on how this works. Our ball has two forces applied to it. We're going to call both these vectors vector A, vector B. Vector A is 5 newtons at 15 degrees west of south, and vector B is 15 newtons 15 degrees east of south. What are the x and y components of the vector? In this situation, a couple things that I would want to note about these two vectors. One, that if I could, well, first of all, I want to have a general idea of where these vectors are located. So in this situation, if I were to utilize the mouse here, let's just do this instead. This guy right here is going to be 15 degrees west of south. That's west of the south mark. So this guy is somewhere like right here, just to give you an idea. Not looking to be proportional or anything. And then this guy is 15 degrees east of south. So that's going to be like right here. So they're both kind of similar. One's on one side of the south line, and the other one's on the other. I made this one longer because it's got 15 newtons versus 5. And I know that's not proportional, but just so we know, that's where these two things are at. And if I could add these two together just by literally putting one of these guys' heads and tails on the other one. But because they're not forming a right triangle, the mathematics on that's a little more challenging to actually figure out the new resultant. What I'm saying here is that if I were to take this vector and place it head to tail, assuming that's head to tail, then I would have a hard time figuring out the new line hooking those two together, which is really what we're doing. That's my new resultant, and that would be my new angle. My new angle is going to be a little bit to the right of the south line, and get myself in view here a little bit. So this would be actually the new resultant would be right here, if those lines are proportional, which of course they're not. Okay, this would be my angle relative to the south axis, and this length of this line would be my actual magnitude, if those lines are proportional, which again I said they're not. Okay, so this problem is a level 2 problem, and it's level 2 because all it's simply asking me to do is break these things into components. Okay, so I am going to take each of these vectors and just use SOHCAHTOA and break them into their x and y components. To do that, I would just complete the triangles on here. It's on the next slide here, I'm sure as we're going well here. Okay, so to do that, I'm going to first of all, sketch them out so we know where they're going. Before we get too far into the actual SOHCAHTOA and the math in this, very, very important thing to kind of understand is that each of these has an x and y component. Here's one. Hopefully it works out here. All right, we have a y component right here. All right. Notice it's going down. That means that's a negative component. And this one's going to the right. So it's going to have a positive component. So as soon as you see this vector, understand I have a negative y and a positive x. I have at that point again a negative y and a positive x. Okay. All right. So at this point, a couple things I'll put in here to start filling my mag table out. This is a pretty common table to use. This is my magnitude, and the angle. Now, when I fill my angles in, I want to use the absolute angle. All right, and the absolute angles I have listed right here. This guy is going to be 200. Well, this guy is the 200 and must be the bigger one. I must have them backwards here. All right, so this guy here is the bigger one, and that's east of that. So this guy is going to be 285. 285. All right, and then this one right here is 255. All right, that is their absolute angle. Now, when we do this, there's a reason why we use these things. Now, I can go with straight SOHCAHTOA, and I know this guy here, I know this angle. This angle right here is 15 degrees. This angle is 15 degrees. And of course, the angle on the other side is also 15 degrees. Now, one really nice thing about using absolute angles is that if you use the absolute angle, then the formula is always the same, and you always get the correct x and y components, and you always get the correct sign. Alright, so what is that formula? Well, it's going to be the cosine. Get this a little bit bigger here. It's likely on the next slide anyways, but it's going to be the formula, and I'll pump it in here, is the cosine, well, the magnitude of the vector times the cosine of the absolute angle, which is 285. That's from the 0 point, all 90, 180, 270, 15 more degrees, 285, which is why I knew that this was backwards. This one's bigger than 270 by 15 degrees. This one's less than 270 by 15 degrees. So this is going to be 285 equals. This will give me the x component of this guy. The sine, the magnitude, which is 15, times the sine of the absolute angle, 285, equals, right? And then that gives us our y component. This will be done exactly the same as we move into the other vector. One thing different is a different magnitude, which is, take this out, we can put in the actual magnitude, which is going to be 15 for this guy. So let's do that. It'll be on the next slide. So let's see the math here. All right, so these are my absolute angles, and there we go. All right, so as I got these guys, how did I get these components? Okay, I just briefly talked about it. In fact, I'm going to grab that. I'm going to grab this. All right. All right. That's good enough. All right, so how do I get that? Well, what I do is I plug in for the, let's say, vector B. Then this is going to be the 15 and equals, in this case, is going to be 3.88. And then for the y component, it's going to be 15 times the sine. And this is just a shortcut SOHCAHTOA. All right, negative 14.4. Now, if you use just 15 in here, you're going to get the same, well, you should get a similar number, similar numbers. You might, your y might not being x, your x might be y, you may get those backwards, and your signs are all going to be positive. So this is what one of the benefits of this particular model. All right, this is for vector B. All right, so now vector A is exactly the same. I'll just repaste this on here, and then we will grab it and readjust it for vector A. All right, now the magnitude is going to be 5, and then the angle is going to be, well, 255. 255. Notice those are in the right spots there. And then that is going to give us, do the math on that thing, it's going to be negative 1.29. And then here it's going to be the magnitude, which is going to be the 5, and times the 255 equals negative 4.8. Okay, 2 if you'd like. All right, so that's the math on how we got our two components. Okay. So the next question, which is level 3 question, is what is the resultant force the ball feels? Now, in this situation, when we have two forces applying to this, right? This is only a level 3 question because it involves multiple pieces coming together. So we're going to take the level 3 question involves this option of breaking two components apart that aren't at 90 degrees, and then plugging them into a mag table, adding them up. Now the 2.59 and the negative 19.2 represent, as you add them up, all of the x component and all of the y component. Okay? So at this point, a lot of the hard work is already done, but let's look at this last piece. How do I rebuild? I always call it you break apart, you add it together, and then you rebuild it. All right, so in this situation, all right, let's go to the next slide. Okay, so I have these two components. I want to rebuild them. I don't like using a model like we used in just a previous little bit ago for getting the XY components if it isn't easier. You don't need a model for this particular piece because the XY components are right there for you. So what we're going to do is take my new X and Y and just rebuild it. All right, let's use an arrow. Let's make that arrow orange. All right, so all I got to do is draw out. I have a to the right. Now, why am I going right? 2.59? Because it's positive. Now, I'm going to go down 19.2. Now, again, I'm not making this proportional. That's fine. A little bit longer. This is a little bigger number. And then my new component is simply going to be the two connected between here. Now, I can go with this angle or this angle. Doesn't make a difference. This angle is one angle. This angle here is actually this angle right here. All right, so, all right, let's do the math on that. I'll use Pythagorean theorem to get the 2.59. All right, and I'm not going to be doing a ton of this, but 2.59. I'll give you the answer here in a second. All right, this guy is now it's negative 19, but in this point, that the negative just means down. Negative 19.2, and we want to solve for that guy. Now again, I just need to use Pythagorean theorem for that. Okay, and I'll use the trig functions for the angles. You'll see that in a moment here. All right, and there we go. So here is the Pythagorean theorem. Now I want to just make sure I square root this thing right here, giving me 19.3. This is my again. This is short. This is short. I have a little longer. It's short. So this guy is not much longer than the 19.2. In fact, only 19.3. And you'll see my angle here is actually 82.3 degrees south of the east mark. This angle right here will be subtracted from 90. And I have 19. Yep. Well, it could be 82.3 minus 90. Should be able to do that in my head. Equals 7.7. So this bottom angle would be 19.3. So our total magnitude, okay, 7.7 degrees. Okay. 7.7 degrees. All right, that would be east of south. Okay. And that is it. You could also call that thing an absolute angle 277.7 degrees, which is 7 degrees past the 270 mark. This is kind of our baseline problem. Level 3 would be something that we would want every single person to be able to do as we go through this class. Taking the vectors, breaking them apart, adding them together, and rebuilding a new vector. Thank you very much.